Good afternoon, and welcome back for those that were here this morning. And looks like we have a few more to join us. If you're not here this morning, my name is Wayne Hurwitz from Northrop Grumman Systems Corporation here in Southern California, and I am the Industry General Chair for this year's Joint Propulsion Conference. After this morning's sessions, I hope you all agree that we're off to a good start. I was happy to see full sessions, papers being presented, the great keynote and panel session this morning. And one of the things that made that possible was the great help from our organizing committee. I want to once again thank my JPC government co-chair, Jimmy Kenyon, from the Office of the Assistant Secretary of Defense for Research and Engineering. Our general chair for this year's IECEC, Ted Stern from Vanguard Space Technologies, and Ashwana Gupta from the University of Maryland, our current director for the AIAA Propulsion and Energy Group. As I said this morning, we got a lot of help pulling together this year's program, and once again, I would like to thank all the volunteers, including the conference technical chairs, topic area organizers, and our sponsoring societies, the AIAA staff, and our industry sponsors as well, who made this all possible. So continuing our JPC theme, Design, Test, Fly, Turning Propulsion Ideas to Reality, our keynote speaker and panel this afternoon will continue today's theme of space and high-speed systems. Tomorrow again, we will turn our attention to propulsion for aviation, and Wednesday we'll talk public policy and our test infrastructure. In parallel sessions, continuing on will be our IECEC theme, continuing to offer topics on government, academia, and industry working together towards clean energy. So there's lots of topic areas for everyone to participate in. So you don't want to hear me speak anymore, so now to introduce our keynote speaker for this afternoon, I invite to the podium our past AIAA president and the Willis Young Professor and Chair for the Department of Aerospace Engineering at the University of Maryland, Dr. Mark Lewis.
Well, thank you, everyone, and welcome to what is already turning out to be a spectacularly successful Joint Propulsion Conference. I know none of you are actually here to listen to me this afternoon, so I'm going to make my remarks as briefly as possible, and those remarks will be to introduce this afternoon's guest speaker, Mr. Elon Musk. Truly an individual who requires no introduction, but please indulge me because I'm going to offer him one anyway. Elon Musk, as I think you know, is the CEO and the inspirational force behind the company called SpaceX, which has made quite a name for itself. He has a very, very impressive background. Born and raised in South Africa, he was the son of a South African engineer. His mother was from Canada. At the age of 17, he decided America was the land of opportunity. So on his own, moved to Canada and the United States, lived with family, did a variety of odd jobs, including working on a wheat farm and cleaning grain bins, was accepted in 1992 to University of Pennsylvania's Wharton School, and also studied physics at the University of Pennsylvania. From there, he went to graduate school at Stanford, where he explains that he basically spent 2 days as a graduate student and decided that there are better things in life. Went on to, and which some of us in academia would hardly agree with, don't quote that in front of any of my graduate students, went on to found a company called Zip2, which provided online content publishing software for news organizations. Sold that company, and whereas I think most of us in this room would have retired, went on to found an even bigger and better company, PayPal, which I'm sure many of you are familiar with. Elon sold PayPal, and I think he decided all he ever really wanted to do was build electric cars and build space vehicles, and he's managed to be able to do both. In June of 2002, he founded Space Explorations Technology, SpaceX. He's currently the CEO and the CTO, very impressive dual role. And of course, SpaceX develops and manufactures space launch vehicles. Perhaps their best known products are the Falcon 1 rocket and most recently the Falcon 9 rocket. He is also famous for his role in leading the Tesla Motors Corporation, building electric cars, and perhaps the first truly operational electric cars that's, I think, been an inspiration to the rest of the automotive industry. And he is also the primary investor and chairman of the board of Solar City. It's a photovoltaics products and services company that is providing electric power services, planning to do so throughout the United States. If I went through a list of awards and recognitions, it would also, I think, fill most of the allotted time. I'll just hit some highlights. In February of 2011, Elon was listed as one of America's 20 most powerful CEOs, 40 and under. He was listed as one of Time Magazine's 100 people who will most affect the world in 2010. He is a recipient of our very own AIAA George Low Astronautics Award, presented for the most outstanding contributions in the field of space transportation. He got that in 2007, 2008. And he's on the Caltech Board of Trustees. Perhaps most impressive, at least in my mind, is in 2010, a survey by the Space Foundation ranked Elon as the number 10th most popular space hero, tied with Dr. Wernher von Braun. He's also, I think, is very well known, the inspiration for the fictional character of Tony Stark in the Iron Man 2 movie. So, without further ado, let me ask you to join me in welcoming Elon Musk to the podium.
Well, thanks very much for having me and for the kind introduction. I think we've got a video that's maybe a good way to kick it off, is just to play the video if we could.
Liftoff. Liftoff of the Falcon 9.
So I'll maybe just give a little bit of background as to why I'm doing this. And I think some people maybe have heard part of the story before, so I apologize if some of it seems repetitive. But I started SpaceX 9 years ago, almost exactly, nine years, maybe 2 months ago. The reason for it was I was really concerned that we were not on a path to become a multi-planet species and a spacefaring civilization. If you look at what our capability has been at various points in time, and you extrapolate that, it doesn't go in a good direction. I mean, in 1969, we were able to go to the moon. And then in the 80s, we were just able to go to low Earth orbit with people. And of course, now we cannot even go to low Earth orbit with people. Although hopefully in a few years, we'll be able to do that on our spacecraft and maybe other spacecraft, other American spacecraft. But clearly something needs to be done to reverse that trajectory, or the future of space is extremely dismal. So that was the reason I started SpaceX with that aspiration, but it was a very difficult thing because I'd never built anything physical before. I'd done a lot of software. Actually, technically, I'd built rockets when I was a kid, but with mixed success. In South Africa, they didn't have Estes rockets, so in order to make a rocket, you have to mix your own grain and get all these ingredients, it's actually pretty hard to create a solid rocket propellant and get it all right. So, but some of them worked. But apart from like stuff as a kid, that's the first time I made anything physical was SpaceX, so I had to kind of figure out all the elements of what go into a rocket. How do you make the engines and the structure and the avionics and the guidance and control and all that. So it took a little bit of time to figure that out. And then we reached orbit with Falcon 1, basically, I guess it would have been 6 years after starting the company. So that took a while. But since then, our momentum has increased quite a bit. And then last year, we got Falcon 9 to orbit and then took Dragon to orbit and brought it back safely. And then hopefully, if all goes well, this year we'll be docking with the space station in December. So we're focused on that. That's our current top priority. And then our other big priority, of course, is making sure that we can satisfy the Air Force NRO for space launch. In fact, after we get to space station, that will be our top priority, is really convincing the Air Force and NRO that we're a good vehicle. And all of these things are important revenue streams because they're needed to fund future developments. We've got obviously Falcon 9, Falcon Heavy. We've got the Merlin engine, which is about to go through its fourth iteration with the Merlin 1D, and it's the highest efficiency U.S. hydrocarbon engine ever to see flight. And then we'll probably be able to announce, maybe late this year or early next year, a new engine development that we're going to do, which is going to be very exciting, and that'll be a super high efficiency staged combustion engine. We want to make sure we have all our ducks in a row before we announce that development. But I think that's going to be very exciting. And also, something like that's very important for if we want to take significant amounts of cargo and people to Mars. Because I think ultimately the thing that is super important in the grand scale of history is, are we on a path to becoming a multi-planet species or not? And if we're not, well, that's not a very bright future. We'll simply be hanging out on Earth until some eventual calamity claims us. So that's really the important thing, and so that's kind of how I'm judging SpaceX. Like, are we helping move things in that direction? And in order to have a self-sustaining civilization on Mars, you have to be able to transport probably hundreds of thousands, maybe millions of people, and millions of tons of cargo. So clearly, very significant breakthroughs are needed. And I think the most fundamental breakthrough is a rapidly and fully reusable rocket. Those are important qualifiers. It doesn't help if it's partially reusable, and it doesn't help if it's not rapidly reusable. Because if you think of any other mode of transport, like really any mode of transport, from bicycles, cars, planes, boats, they're all rapidly and completely reusable. I mean, apart from occasional maintenance items. So, that's why they function well. You know, if you had a car where you had to, say, you know, replace the tires on every trip, or you could only use it once a week, that wouldn't be a very good car, or plane, or anything. So it's got to be fully and rapidly reusable. Just like when the Wright brothers created the airplane, they actually didn't invent something that flew. They invented controlled powered flight. That was really those are really what made an airplane very useful. So that's something that either SpaceX or some organization has to invent. I think that's a critical element in revolutionizing space. If you look at, say, the Falcon 9, the cost of propellant on Falcon 9 is about 0.3% of the cost of the mission. So, you know, that means if we could fully reuse the vehicle, I mean, it's at least a 2 order of magnitude increase in the cost efficiency of the flight. You know, or sort of another way, you know, it's one thing to ask for, say, 0.3% of the GDP to establish life on another planet. It is another thing to ask for 100% of the GDP. That it will simply not occur. People need food and things, you know, basic stuff like that. So that's something that I think is also an important long-term thing that has to occur. And in that regard, I'm a fan of vertical takeoff and landing because obviously, if you're going to go to other places in the solar system, you know, there's no air on the moon and there's no runways, so wings are not a great idea. Yeah, so those are sort of the things that we hope to do in the future, and we're hiring a lot of people. Last year we grew by 50% in personnel. We're continuing to grow rapidly this year, so we're now about 1,500 people. Yeah, and we have significant operations in Florida, Texas, and California, and in the DC, Virginia area. So we're always looking for great talent, so if anyone's interested in joining SpaceX, please send us your resume. Let's see, I think with that, I'd be happy to open the floor to any questions you have. Sure.
Are you going to be using which specific vehicle to travel to Mars? I mean, you saw this in the video. Do you have an architecture planned out for the Mars trip?
So the question is, do we have an architecture planned out for Mars trips? We do. I wouldn't say it is fleshed out to a detailed level, but we know what the ingredients are, you know, which is a vehicle that's capable of delivering substantial mass to the surface of Mars, and then returning to Earth as well. But I think we'll take this in steps. Certainly, something like Falcon Heavy could deliver, you know, decent payload to the surface of Mars. It's sort of on the order of 12 to 15 metric tons. So that's not bad. I think you probably want a vehicle that can deliver something on the order of 50 metric tons, you know, and be able to do that in a fully reusable manner. Then the whole equation works. And there's more than one way to skin that cat. Yeah, that's what I think.
Yes, I have a question on the reusable vehicle that you talked about. I've seen a lot of studies of these vehicles, and the key to making it work seems to be to get on the order of 200 or 300 missions a year to keep the cost down. What do you see as the commercial drive that will result in the need for 200 or 300 launches a year?
Yeah, I mean, it's always a tough question to answer, and I suspect in the early days of airplanes, people didn't imagine that there would be this many airplane trips. But I think the biggest driver for that is really a base on Mars, or potentially a base on the Moon. I don't think there's really a need for that many satellites, for example, and I also don't think that there's a rational basis for doing things like mining helium-3 on the Moon, or really, I have a hard time imagining mining anything anywhere and bringing it to Earth, because Earth has got a lot of stuff. Earth's crust has got almost Earth is big. But I do think there is a market for people who would want to move to the Moon or move to Mars, and that I think is interesting, and could support a huge number of flights, thousands of flights a year.
Can you tell us your plans for the Dragon capsule and how you plan to start getting astronauts and maybe support the space station?
Sure. Question just about our Dragon spacecraft and what we're going to do with respect to transporting astronauts and whatnot. We actually designed the Falcon 9 and Dragon to meet the published NASA human rating design guidelines. So, things like designing to a 1.4 factor of safety instead of a 1.25, having being multi-failure tolerant. So a Dragon, for example, can lose any two engines at any time and still be safe with respect to the space station. Can still translate and rotate as needed. We actually have a sort of a secondary heat shield behind the primary heat shield. The avionics, all two-failure tolerant, all that sort of stuff. It's got windows. So the question is, well, what doesn't it have? Really, the main thing is just the escape system. So in terms of upgrading it, we need to add a launch escape. And in this, we're taking a sort of a different path than has been done before, which is to tap the onboard propellant, which is NTO-MMH, as escape propellant. Because you either need to maneuver on orbit or you need to escape. You don't need to do both. And this makes for a very mass efficient design. It also means that you can carry high velocity escape capability all the way to orbit, as opposed to having to dump a launch tower kind of early on. And then a sort of optional bonus is we can use those same engines to land propulsively. Now we're still going to retain redundant parachutes on Dragon, so you still have redundant parachutes. So effectively, you'd have almost 4 levels of redundancy because the landing engines are themselves redundant, and then you've got redundant main parachutes. So like 4 things would have to fail before. Actually, only on the 4 things in a row would have to fail before loss of life. But then the neat thing about that is you could use it to propulsively land in other places like Mars or Moon or somewhere. So I think it's got potential as a generalized science delivery platform for other missions in the solar system. So the question is, where do I see electric propulsion? I think that's actually that's for sure a good idea for interplanetary travel, particularly since you're going to need a lot of energy once you're on the surface of Mars. So you may as well use that energy while you're in transit to speed up the journey. So I think electric propulsion definitely is a good idea. And it would be kind of a waste not to do electric propulsion on the way there. The trick is you want to obviously have electric propulsion with enough thrust to matter. That's pretty important. yeah, I think and needs to be fairly efficient in terms of the energy per newton, like I guess watts of energy to newtons of force. So. So, I mean, the capsule does have an LOD. You know, that it has depending upon where we put the lateral center of mass, we can adjust the LOD to as high as 0.3. So that gives us a pretty good accuracy. In fact, Dragon landed to within about a mile of its target on the flight in December. And you know, there's not an obvious reason, I think, to have more LOD than that. Yeah, nothing that I can think of. And then, you know, the problem with having more complex lifting bodies is that then it gets kind of weird if you want to go to Mars, you know, and Mars has a much lower energy, atmospheric density, particularly in the lower atmosphere. So you know, something that worked well on Earth wouldn't necessarily work well on Mars. It obviously would be completely useless on the Moon. So I think, you know, something with a 0.2 to 0.3 LOD is I think good enough, and it's very robust as well. You don't have to worry about maintaining a specific angle of attack. Or something going wrong with your control systems or anything. Even if Dragon control systems totally malfunctioned and were just dead, you still survive because it's going to naturally orient with the main heat shield down. You'll experience higher Gs. You know, you might see 8 or 9 Gs instead of 4 to 5, but that's the only downside. And you can manually pull the chutes. So it's very, very robust in that sense. Sure. Yeah. So for Falcon Heavy the cross feed between the outer cores to the center is pretty helpful. You know, it gives roughly 20 to 30% more payload, and we have an advantage here in that because there are 9 engines. We can control flow to those engines individually. So the way we would do crossfeed is to basically draw propellant for the engines that are adjacent to the core from the you know, so the engines that so the center core engine is pulling from its side core on either side. And then we can shut pre-valves to those engines so that it's not sucking it down from the side cores. You can't do this if you've got one engine, or if you know, but you can do it if you have multiple, 9 engines. It's a lot easier. But the crossfeed is really an option for really big payloads. So for customers that don't need the crossfeed, we would not enable crossfeed. Yeah, but it's helpful for missions to the outer, either big missions to Mars or missions to the outer solar system. So we're talking with NASA about some potential missions that go out, to 150 or 200 AU. So you're sort of way out past Pluto and stuff. Yep. Well, this question was just generally, how's it gone with reusability? Well, so far it has sucked, really. I mean, it is extremely difficult. And there's a reason that nobody has invented a fully reusable rocket before. It's super damn hard. But we have learned a lot, we did recover Dragon. So if you sort of think of Dragon as a third stage, we have recovered Dragon, and we recovered it in a condition that you could easily refly it with changing nothing. You know, repack the chutes and you can fly it again. But the thing is, we can't afford to give a Dragon level of protection to the booster, or the booster would get no payload to orbit. So the real tricky thing here is essentially, you know, constructing a suit of armor that is just exactly tailored to the forces it's going to need to resist on reentry. And those forces are higher than we anticipated. Even for the first stage, because of the trajectory of the first stage, it comes in at a pretty steep angle. So the force is very high. It's basically belly flopping on the atmosphere. So something has to be done to shed velocity. So we're looking at potentially restarting the engines to shed some velocity and give it a more benign reentry, weighed against increased structural margins and increased and a better thermal shield. It's a tough trade on propellant versus dry mass, and I think we've got something that on paper closes, and we'll see if that turns out to be reality as well.
You spoke about the need for hundreds of thousands of launches per year to get the real economics to serve this, and the moon base and Mars base being able to justify that. And what I'm wondering, for a Mars mission, you don't want that surge to be 2 weeks every 26 months, or the economics break down. You talked a little bit about electric propulsion for non-minimum energy transfers, but how do you see this architecture working so that you can support Mars base with the missions spread over all time instead of in discrete increments?
Right, that certainly is one of the biggest challenges with establishing a self-sustaining civilization on Mars is that planetary alignment. So clearly we need to widen that window. I think maybe if we can get it to maybe 6 months, and obviously you're going to put more payload to Mars if you're at the center of the 6 months than if you're 3 months on either side. And that's something where electric propulsion could be pretty helpful. Another thing you can do is you can obviously launch ahead of time into high apogee orbits, so that there's a whole series of craft kind of in a high apogee parking orbits, waiting for the alignment to occur, and then you kick it over to you give that final kick once Mars is close enough. But certainly it is a tricky thing, and it's hard to imagine how opening that window more than about 6 months, and even that is pretty tricky from a delta V standpoint.
Would you like to comment on any downside to the transit time to Mars with chemical propulsion as compared with nuclear propulsion?
Well, the tricky thing with nuclear propulsion is getting that reactor up there with a ton of uranium. I think it's going to be hard to convince the public that we should launch large reactors into space because of the potential for a failure spreading uranium on Earth. It's one thing to do sort of a small RTG, but another thing to have a big reactor. I think at some point you could probably construct a reactor maybe on the Moon or Mars, and then have that power. But also, I think when people sort of think about nuclear reactors, they kind of forget how heavy they are, and also the fact that they usually have a source of water close by to drive a steam turbine. So you know, when you factor all the, like a really useful reactor in space, and see how much it weighs and compare that to, say, solar panels, solar panels are pretty good. It's a different story for Mars itself. I think Mars, on the surface of Mars, a reactor would be great because generating all that waste heat would be, you want waste heat on Mars. That's great stuff. Also want anything that's going to cause global warming on Mars, that can be shipped. So the question is, what do I think about grabbing the oxidizer on the way through the atmosphere? So, like, if you have a hydrogen-oxygen system, and then and having it sort of grab the oxygen on the way. You know, when I've looked at the numbers, it always seemed as though the drag was so significant that it outweighed the benefit of grabbing oxygen. It might be a different thing if air wasn't sort of 80% nitrogen. But when you're grabbing stuff, you're actually grabbing 80% stuff you can't use and 20% stuff you can. And then of course you're sort of stuck in the situation that you can only get a lot of air when there's a lot of drag. And so if you can't really do the high acceleration, and you go past a certain velocity, and the heating rate is too extreme. So you just melt yourself. So I think carrying the oxidizer is probably, even though it seems like, wow, I've got a lot of oxidizer on this rocket, is probably the way to go. I mean, certainly somebody could prove me wrong, but so far I've not seen anything even on paper that would work. So if it doesn't work, at least on paper, then, well, reality is usually worse than paper.
Yeah, question. Stan Borowski from Glenn Research Center. Your comment about the nuclear rockets, for example, you said they were heavy, and that is definitely a fact. Nuclear engines have a tendency to be heavier than chemical systems, but the fact that you get a 100% increase in ISP over the best chemical rockets that we have today, you wind up saving hundreds of metric tons of propellant on these, 6-month round, transits back and forth. So, when you think about it, you really have to think not just of an engine. The engine is only one piece of the overall stage in the system. So that's one thing. I didn't want the audience to kind of think that nuclear rockets are somehow just too heavy and that they have radioactivity in them. When you launch them, they're relatively clean, and there is more radioactivity in the 3 RTGs that were on Cassini's 3 RTGs than there are in 3 25,000-pound thrust nuclear rocket engines to send humans to Mars.
Okay, that seems surprising. Okay, well, if it's really such a small amount of radioactive material, then maybe that could work for an upper stage of a rocket. I think it's a tough thing to do. I'm scared of doing that with the public, basically. If other people may be braver than I am, but I think if I were to raise the idea of launching thousands of nuclear powered rockets, there would be people trying to lynch me.
Well, remember, we're not launching. I mean, when you launch them, they're inert, they're safe, they've got control drums in, and it's natural uranium. There's no radioactive fission products because the engine hasn't been turned on yet. So it's only once they're up in space in a stable orbit that you can unlock the interlock control drums and then start bringing the power up. So NASA's looked at a lot of this stuff, for quite some time.
But what if it crashes, though?
Sorry?
What if there's a launch failure?
Well, there certainly could be a launch failure, but the stage is located way up on the top. It's not in a cargo bay like on the shuttle where they're worried about implosions or collapses and a lot of heat. So, and again, like I said, even if it were to disperse and break open the core, the fuel is, there's virtually little radioactivity in it at all because it's never been operated.
Okay. That sounds like it could be a better option than I thought.
Okay, well, we'd like to talk to you more about it in the
Okay.
future. Thanks.
All right. Yeah, I'm certainly open to if new different ideas, and that's certainly different than I thought it was. Right. Yeah, no, it's actually surprising. I mean, there's obviously this nuclear-powered craft right here in San Diego. So, and nobody seems to get too alarmed about that. Nuclear-powered submarines and stuff. So, yeah, I mean, perhaps the public concern is less than I think it is. People do seem to get alarmed about establishing a nuclear reactor for whatever reason, on the ground. And in the past, they've been upset about nuclear launches, but maybe if a clear case can be made that it's safe, then maybe it's a good way to go. Yeah, I love the idea of fusion. I think fusion is awesome, and I mean, if somebody were to do that, that would be very cool. Yeah, I mean, we need to make fusion work on the ground, in an energy-positive way first, but which in and of itself would be a huge boon for humanity. Yeah, so yeah, it'd be tremendous if somebody sorted that out. Well, our main goal is to establish a means of getting to and from Mars, and then I think if there's that ability, then that will open up opportunities for many organizations and many facets. So it's kind of like if you can get the Union Pacific Railroad across the country, then think of all the businesses that prospered in California. But in the absence of a means of getting there, then there's no opportunity for businesses or organizations to flourish on the other side. So that's our focus is really just can we establish that transportation link and then keep iterating and innovating to make it better and better. That's our sole focus, really. Yeah.
I was wondering if you could talk a little bit about the relationship between government and private industry in getting to Mars.
Well, I think it's definitely going to be a joint effort, and even as it is, in terms of the progress that SpaceX has made thus far, I mean, we would not be where we are today without NASA. I mean, NASA has been a key part of our success, and will continue to be. And obviously, we're hopeful that the Air Force and NRO will become a partner as well. So it's very much a joint effort, and hopefully other companies too. I mean, it's not as though I think it should just be SpaceX. I think there need to be multiple entities that are doing that transport.
What kind of cost per kilogram of orbit do you think we need to get down to make a Mars architecture viable? How far away are we from that?
So the question was, what cost per pound or per kilogram do we need to get below in order to make Mars viable? I mean, so I think in order to make a self-sustaining civilization possible on Mars, we have to get the cost per pound well under $100. Cost per pound to orbit well under $100, probably closer to $50. Now, the thing is that Falcon Heavy, the cost per pound to orbit on an expendable basis is about $1,000. So if we can make Falcon Heavy reusable, depending upon how much payload we lose in the process of making it reusable, that could get to that number. So we'd have to basically improve it by about a factor of 10, maybe 20 to get down to the $50 point. And when you consider that the cost of the propellant is, about 0.3% of the cost of the rocket, or 1/300th, then it's, as long as it should be possible to do that even with a Falcon Heavy. But this will take a long time to get. It's a long time by definition, meaning like several years. Sure.
Are you considering architectures where you have an interplanetary vehicle that once up always stays up, say between Earth and Mars, and then on each end you have descent-ascent vehicles which are like taxis, or if you will,
right,
rental cars, to get you to the major.
Yeah, I think long term there probably is some architecture where there are smaller craft that take you to Earth orbit, do back and forth from Earth orbit and Mars orbit, and then there's some sort of much larger ship that's circulating, or ships that are circulating between Earth and Mars. I think that's by longer term. I mean, I think that, so that's, in several decades from now, I think that's probably the right thing. But in the interim, I think it's probably going to be more like it's one ship that takes you to Mars and back. I think that's kind of the short to medium term solution. And now the nice thing is that as soon as you have a base on Mars, you've got a forcing function for improving the transportation technology. Just like when, before the United States colonies were established, there was no forcing function for improving trips across the Atlantic. But when they were, then suddenly there was a need to have those ships be better and better every year. And so ship technology improved dramatically because of that forcing function. I think the same will occur if there is a base on Mars.
Hi, I'm Matt Vlasic. I was curious about, to establish the initial base on Mars, to get that initial thrust, do you think it'll be mostly government funding? Do you think it'll be private and government, or will it be like an X Prize sort of thing?
Be a hell of an X Prize. I think it's some combination of government and private, it's hard to say exactly what percentage, but I think it's a pretty sure bet that it'll be a combination of government and private enterprise. Unlikely to be an X Prize, but there may be elements of it that are X Prize-ish.
So once you begin sending people up into space, and until it becomes a sort of mostly commercial endeavor, do you, I assume mostly you'll be sending NASA astronauts up to the space station. Do you have any missions that you're specifically interested in? Would you be training like your own astronauts, or would it mostly be using NASA to do those sorts of things?
Well, I mean, NASA would be our customer as far as transporting people to the space station is concerned, so it would really be a decision of NASA as to who goes on. I mean, I think it's going to be NASA astronauts that fly on those trips. It'll be whoever our customer decides. It's sort of, it's like buying a flight of an airplane or something. It's up to the customer to decide. I think we will also have private astronauts that want to fly either to a private space station or maybe on trips around the Earth, or conceivably a loop around the Moon. All right. Thank you very much.
Let me thank Elon for a very stimulating presentation and question and answer. And of course, to thank you for your time and also your service and support of this conference, we have the coveted AIAA coin.
Thanks.
Elon, thank you so much.
All right, thank you.
And that concludes this keynote. Thank you all very much.